In this mini lecture, we're going to introduce three different types of forces that we're going to encounter a lot during this week and next week. And then we're going to work on a problem where we have an accelerating system, and we're going to use Newton's second law and also a little bit of Newton's third law too. So this first force that we're going to talk about is gravity and weight. Gravity is an external force. Your weight is the force that the Earth's gravity exerts on you. So sometimes I'll write it as W for weight is equal to your mass times gravity. But this is also a vector too, so you could put vector arrows on top of it. The weight is equal to the mass times gravity. The agent of this force, that's the thing that's doing the pulling, is the entire Earth pulling on an object. The entire Earth is pulling an object towards the surface of Earth. An object's weight vector will always point vertically downward towards the surface of the Earth, towards the center of the Earth. Your weight is proportional to your mass. It's the mass times the acceleration due to gravity, but it is not the same thing as your mass. Your mass is how much stuff are you made up of, and then your weight is an expression of how much force is the Earth exerting on you. So here's an example of a basketball, and we have the weight vector drawn in. And so no matter where the basketball is, whether it's moving up or down, or it's on the ground, or it's rolling around, that weight vector is always going to be pointing downward towards the surface of the Earth, or downward towards the center of the Earth. Another example of a force that we'll encounter is what we're going to call tension. So in this example here, we have a sled and there's a rope attached to it. This rope exerts a tension force on the sled. So usually we use tension forces when we've got a rope or a cable or something that's pulling on another object. And then we would represent this vector. Sometimes I label it as capital T for tension, usually meaning that that's a pulling force. So when a string or a rope or a wire pulls on an object, it exerts, this is a contact force that we're calling the tension force. And the direction of this tension force is always in the direction of the pull on the string or the rope. So this tension force, since we're pulling up in this direction with the string on the sled, the direction of this tension force is also going to be directed along the string or the rope or the cable. And the final force we're going to talk about today is called the normal force. Normal doesn't mean, in this case, average or usual. Normal here means perpendicular, 90 degrees with respect to a surface. The normal force is the force exerted by a surface against an object that is pressing against the surface. So here we're going to take this bag of dog food and we're going to put it on a table. And when we do that, this object, this bag, has a force acting on it, gravitational force. That's its weight, and that's always directed downward towards the surface of the Earth. So this would be the mass times gravity of this bag here, directed downward towards the center of the Earth. And then we have the normal force. The normal force is the force that that table is pushing back up on the bag with. Okay, that's the normal force. So here they're representing the normal force as a capital N. Sometimes I represent it as a capital F with a little n subscript. So the force exerted on an object that is pressing against the surface is in a direction perpendicular to that surface. So that's why we call it the normal force. So the angle here between the normal force and the surface here would be 90 degrees, and that we refer to as being normal. When we're solving problems that deal with Newton's laws, we are going to want to draw pictures. And we're going to want to draw something that we call a free body diagram. Okay, that doesn't mean that it doesn't cost money, but it means that we're drawing all the forces acting on an object. So free body diagrams are an essential step in solving Newton's laws problems. They illustrate all the external forces on a body, on an object. The object is represented as a single isolated floating point. That's your free body. And all the other forces acting on the body are then drawn as vectors. So we are going to draw the free body diagram for an object in free fall, a book on a table, and a box being pulled by a string at some angle with respect to the horizontal, to give you an example of what some free body diagrams might look like.
So now that you know a little bit more about free body diagrams, at least theoretically you know like what the definition of one is, let's see what they actually look like when we draw them out. You're going to have to be drawing a lot of free body diagrams over the next few weeks, and so let's take a look at some classic free body diagrams, some of the basic free body diagrams. So let's draw a free body diagram of an object in free fall. We're assuming that it's falling in a vacuum, so there's no air resistance. So this is my object. It's just going to be a circle, a ball here. And if the object is in free fall, there's no air surrounding it, there's no resistive force. The only force that's acting on this object is the weight of that body. And the weight of an object always points directly down toward the earth, directly down toward the ground. And so this free body diagram, we've got the only force acting on our body, if it's in free fall, no drag, is that we've got the weight, which is equal to the mass times gravity of that object. And that weight vector is always pointing down to the ground because our Earth is trying to pull us down to the ground with a force equal to our mass times gravity. And then another one, we've got a book on a table. So here's my table, and I'm going to put my book on top of the table. Okay, this book, this is the book right here. The book always has also a weight, and so if we're going to think about the free body diagram of that book right here, it also has a component of its weight pointing downward, directly downward, and that is equal to its mass times gravity. So we've got that acting on our object, mg pointing straight to the ground, and then we have the normal force, the force from the table pushing back up onto the book, okay? And we are going to call that force the normal force, normal meaning perpendicular, and I usually represent these normal forces as an F with a little subscript N on it to represent the normal force. And then let's have an even more complicated one. A book being pulled across a frictionless surface by a rope attached at an angle above the horizontal. So here's my frictionless surface. Here is my box, okay? And it's an object, it has some mass, so it's always going to have its weight pointing directly down, and that weight is equal to mass times gravity. It's on a surface, and since we're on a surface, this box also has a normal force, and that force is pointing up, directly upward, normal force. And then we're pulling this box. Maybe there's a string attached to the box here. We're pulling that box by a rope attached at an angle theta above the horizontal. Okay, so here's my angle theta, and I'm going to call this force the tension force. Anytime you're tugging on something, you've got a string here, we've got some tension in the string that's pulling it up this way. So here's our tension force acting at some angle above the horizontal. So the normal force and the weight, the mass times gravity, are both along the vertical axis. And this tension force has a component along the horizontal axis, and it also has a component along the vertical axis. And so we'll have to take both of those into account whenever we solve problems where we're dragging something across the surface like this. So those are 3 examples of pretty basic free body diagrams.
Now we're going to solve a problem which will involve us thinking about the weight of an object, drawing a free body diagram, and then applying Newton's second law. And we're going to do this in a system that happens to be accelerating.
In this problem, we are going to work with something called an accelerating system. I'll explain what that means here. But we have an astronaut, and that astronaut is weighing a 5-kilogram meteorite with a spring scale attached to the ceiling of a rocket ship. So this is a theoretical problem here. So we have then, in this drawing right here, we've got the ceiling of our rocket ship. Here's the scale hanging from the ceiling, okay? And that scale has a little piece, a little metal hook maybe, that's attached such that it's attached to the meteorite, okay? The meteorite has a mass of 5 kilograms. And this scale is calibrated to tell us the weight of this meteorite in newtons. That means that the tension force that's pulling upward on this meteorite, okay, that is being read here by the scale. Okay, so whatever this tension force is that's pulling up on my meteorite here is being measured by the scale, and then that is calibrated to output the weight of that object, its mass times gravity, assuming that we're on the surface of the Earth, okay? So what happens whenever we accelerate? What happens if this rocket ship decides to zoom up with an acceleration of 2 meters per second squared? So if that rocket ship accelerates up, that means that the roof is accelerating up. That means that the scale is accelerating up too. And that's going to change the measurement for the weight of this meteorite right here, okay? And so our question is, what does the scale read if our rocket ship accelerates upward at 2 meters per second squared as it leaves the Earth? Okay, so we're going to approach this problem in 3 steps. The first step, we're just going to calculate what the meteorite's weight is right now, stationary in the rocket ship. We're not yet moving. So the weight of my meteorite here is just going to be its mass times gravity. And that's going to be 5 kilograms times, we're assuming we're on Earth, so 9.8 meters per second squared. So the weight of our meteorite turns out to be 49 newtons. Okay? So if I were to draw a free body diagram of my meteorite, I have, which is the next step, we're going to draw the free body diagram. I have my meteorite right here. I've got its weight acting downward. Its weight is equal to its mass times gravity. And then it has some tension force that's pulling upward on it. I'm going to call that T, okay? That tension force is coming from the fact that our meteorite is attached by a hook or a string or something to the scale. The scale effectively above here is measuring what this tension force is on our meteorite here. So if we're not accelerating, we're stationary, that tension force pulling upward on my meteorite here and being read by the scale is equal to the mass times gravity of the meteorite. Here's my meteorite. I've got a little ball right here. I'm going to put it here on the end of the spring scale. You see the scale stretches right here. And on one side, I can read the mass times gravity, or the weight of this object in newtons. That's what's happening here, okay? So we've got the mass times gravity of my ball downward. I've got the tension force pulling upward on this ball here. Okay, that tension force is what is being read right here by the spring scale. Now, what happens when you accelerate the system? Imagine that my thumb here is the roof of the spaceship. If I accelerate upward at a constant rate, then what's going to happen is that this tension force is going to change. And it's going to change according to our Newton's second law equation, that the sum of all the forces acting in the vertical direction must equal to the mass times acceleration. And so then you get a situation where if you were to read off the scale what the weight of this meteorite is when you're accelerating upward, you would find that the scale actually reads a larger number than 49 newtons because we're accelerating upward. And you can actually kind of experiment with it to see what happens for the very instant after you tug upward on your spring scale here when you're hanging something on the bottom. At the very instant you tug upwards, you see that the apparent weight of that object becomes a little bit larger. And if you accelerate downward really quick, the apparent weight of that object gets smaller. And that all comes from the sum of the forces equaling mass times acceleration. Okay, so let us solve this problem now. We want to solve for what does the scale read if the rocket ship accelerates upward at 2 meters per second squared as it leaves the Earth. So in order to solve this problem, we need to work with Newton's second law in the vertical direction. That's the only dimension along which we have any motion anyway. So the sum of the forces in the y direction has to equal the mass times the acceleration in the y direction. So from my free body diagram of my ball here, or of my meteorite here, I've got the tension pulling upward that's attached to the scale, that's what the scale is reading, minus the weight of my object, mass times gravity, minus, because that vector is pointing down, the tension vector is pulling up, and that equals the mass times the acceleration of the system in the y direction. So we know that that's that 2 meters per second squared here. So if we solve this equation for tension, that tells us what the scale is going to be reading, the scale that's attached right here. And so the tension is equal to the mass times the acceleration in the y direction plus the mass times gravity. That equals the mass times the acceleration in the y direction plus the acceleration due to gravity. So that equals the mass of my ball, 5 kilograms, times our acceleration in the y direction of the spaceship. That was the 2 meters per second squared, plus our 9.8 meters per second squared. And then we take 5 times, we've got our 5 kilograms times 11.8 meters per second squared, and that equals 59 newtons. Okay, so we see that the scale is going to read that this meteorite actually weighs more when we're accelerating upward, okay? And that all comes from here, Newton's second law, the sum of the forces equals mass times acceleration. A similar thing happens when you are in an elevator, okay? When you're in an elevator and the elevator accelerates upward, you, for a brief moment, feel like you've got a pressure pushing down on you. What that is you, for a brief moment, feeling like you weigh more because you're being accelerated upward.